Hey class, I wanted to do a quick video about problem 13 in case you were having any trouble with it. We've got a ball dropped from a height of 80 feet. Every time it hits the ground, it bounces to 80% of the previous height. So it kind of tries to walk you through the steps of this, but what height will the ball bounce up to after striking the ground for the third time? Right, so part of the difficulty with this problem is that when we drop it from 80 feet, it hasn't hit the ground yet. So if I draw a picture of it, it's falling 80 feet, and then it's gonna hit the ground for the first time right there. And when it bounces back up, it's only going to 80% of that, which would be 80 times 0.8, which is 64. So then we could, repeat that process. When it hits the ground the second time, we now do 64 times 0.8, that'll be 51.2. And after striking the ground for the third time, what height will it bounce back up to? So 51.2 times 0.8 would be 40.96. So after three bounces, it bounces back up to 40.96 feet. What is the height after the nth time? Okay, so what we can see here is that after the first bounce, the height is 64. After the second bounce, there's the height. After the third bounce, 40.96, etc. So we can tell this is geometric because we're multiplying by 0.8 every time. So I know my R is 0.8, and I know my first term, well, let's be careful. The very first term, when there's been one bounce, is 64, right? It's hit the ground one time. So 80 is not our A1, 64 is. So if we're going to write our AN, I'm going to take 64 times 0.8 to the n minus 1. And notice, because it's after it hits the ground the nth time. So after it hits the ground the first time, that should lead us to a height of 64, and it does, because if we plug in 1 for n, we get 0.8 to the 0. After which bounce will the height be 6 inches or less? Okay, well, everything else is in feet, so I'm going to change that to 0.5 feet. And basically, I just want to know, when is that height going to be 0.5? So I have to do 0.5 equals 64 times 0.8 to the n minus 1, and we can solve that on our calculator. We'd get, 0.5 over 64 is 0.0078, which equals 0.8 to the n minus 1. You'd use natural log or just a solver, but if you were trying to show your work here, and you'd get that n minus 1 equals ln 0.0078 over ln of 0.8, and so you end up finding out that n equals 23. So after the 23rd bounce, the height would be 6 inches, and then after that it would be less. What is the total height that the ball travels by the time it is done bouncing? All right, this is the best part of the problem. Total height would be like a sum. So we're thinking a sum, and this ball, every time it's like done bouncing, well, we don't know what n value it's done bouncing. This function would never actually equal 0. So if we plug in n as a really big number, so we're really thinking this is an infinite sum. And we kind of have two situations going on. We have the downs. So the ball goes down 80 feet, and then it bounced back up, which I'll do in red, 64, but then it went down 64, then it went up 51.2, oops, and then back down 51.2, and so on. So I can't really, they're almost like two separate series here. So we're going to have to do two separate sums. So we need the sum of the ups, which for my infinite sum, it's the first term. I guess this should be the sum of the downs because it's blue. Okay, so for my first term, we have 80 over 1 minus 0.8 for my common ratio. And when you do that, you get 400. And the sum of the ups would be 64 over 1 minus 0.8, and that equals 320. So the total distance is 720 feet. All right, hope that helped.